Okay, let us start. Good afternoon, everyone. Welcome to this November edition of the mini-school. My name is Francesco Petruccione, and I'm the director of NITheCS. And today it's a really big pleasure to introduce Shane McFarthing. Yeah, Shane is a PhD student in my group here at Stellenbosch University. And he did his MSc in computer science at the University of KwaZulu-Natal, but already on a topic from quantum computing. Yeah? And today he volunteered to share his wisdom about how to do quantum chemistry on quantum computers. Yeah? And we have a plan for 4 lectures. Today will be just, I think, basic introduction in the many electron setup, yeah, that as we will encounter later on, and slowly we will build it up to how to solve and find the ground states of molecules on quantum computers. Yeah, Shane, thank you very much for agreeing. Yeah, and to our online participants, you know the rules of the game. You're welcome to raise your hand maybe at the end of the talk and ask questions, or just share questions in the Q&A facility at the bottom of the Zoom screen. Yeah. So Shane, thank you very much. I will mute myself.
Okay, thank you very much, Prof, for the introduction. Yeah, so today we're going to be starting off the mini school. And like Francesco said, the mini school is going to be covering the application of quantum computing and classical computing for solving some quantum chemistry problems, specifically the electronic structure problem. And just to kind of start off with laying the context of it, if we just consider the topic of quantum chemistry, this is the application of quantum mechanics to chemical systems. And we particularly do this for the calculation of some physical and chemical properties. And historically, these types of investigations into some properties of chemical systems have been done in a laboratory setting. But this can be quite costly and also time consuming, even though it is necessary in order to validate some theoretical results and some models. But we found that over the past years, as the methods that we have advanced, and so as the computational hardware that we have available, the power of the computational chemistry has really come to the forefront, and it's become a really useful tool for reducing some of the some of the overhead with regards to doing these laboratory investigations. So like I said, they can be really costly, they can take a lot of time to do, and if you're able to use these computational models for doing the simulation of the systems instead on a computer, you can gain some preliminary results that can kind of filter out a lot of the tests that you need to do, and you can also do some validation with actual experiments afterwards. So if we take a look at the mini school and how it's kind of going to be structured, we have 4 lectures, and today's lecture is just going to be on setting the background of the problem. So we're going to be going into a little bit of introduction of some of the chemical terminology that we need to know, an introduction into the electronic structure problem and how it's set up, and some of the industrially relevant applications that we have for this specific problem. And then that'll lead us into the next lecture, where we look at trying to solve this problem with some traditional classical methods. So we're going to look at some methods like Hartree-Fock and some other computational methods before looking at some of the best methods that are available on the classical devices. And that's just our lecture 2. Then in our 3rd lecture, we'll go into more like hallmark type of hybrid quantum classical algorithm, which is the Variational Quantum Eigensolver. And this has been around for quite a while now and is widely studied and used. It has some advantages and some disadvantages. And in this lecture, we're going to kind of cover how the algorithm works and exactly what those advantages and disadvantages are. And that will bring us as an introduction into how we try to solve this problem on quantum computers. And then in our final lecture, we're going to take a look at the state-of-the-art quantum methods that are available and are being studied at the moment. So this includes things like adapt VQE and advancements on the VQE algorithm and some other methods. And the reason for kind of looking at this topic is that performing quantum chemistry calculations on a quantum computer is one of the most attractive applications of quantum computers, and is thought to be one of the possible avenues of obtaining quantum advantage in the near future. So a lot of talks are done on the quantum machine learning and those types of aspects, and the quantum chemistry is another really big field with a lot of really useful applications. So that's kind of the motivation for doing this mini school. So if you want to know what we'll learn over the course of this mini school, we kind of have some objectives laid out for each lecture. And for the first lecture, you're going to have some understanding of electronic structure theory and its applications. Then when we move into the next lecture on the classical methods, we're going to develop a working understanding of how these methods can be applied to solving the electronic structure problem. Then in the third lecture, you're going to have an understanding of the variational quantum eigensolver algorithm and its characteristics, as well as how it'll be set up on the quantum device. So we'll go from the setup of the problem on the quantum device, as mapping to the qubits, and then how we use the hybrid algorithm to try to find the solutions to this. And then lastly, when we move into the last lecture, we're going to try to bring you to the forefront of what exactly is happening in this field on quantum devices, so that you be able to kind of take a look at some of the more recent literature and be able to follow along with some of the discussions yourself. So that brings us to the beginning of our first lecture, which will be on the introduction to electronic structure. So the lecture's kind of broken down into three main sections. So the first one will be the definition and applications. So in this, we're going to kind of lead into exactly what is the electronic structure problem and why do we want to study this, or what are some of its applications? Because we need to know why we would be motivated to even study this specific topic. And then in the second section, we kind of go into a more mathematically formal definition of this problem and what it really means to solve it and what we try to do. And in the last section, we take a look at something called the Born-Oppenheimer approximation, which is a commonly used way to try to reduce the computational complexity of the electronic structure problem. So to begin with, we're just going to take a very brief intro into the chemical background of exactly what we're doing. So we know that atoms are made up of some subatomic particles. So those are the electrons, which are negatively charged, and then the positively charged protons and the uncharged neutrons. And the protons and the neutrons form the nucleus of these atoms. And atoms make up all the substances that we know, and they can interact with each other through a method called bonding. And some common types of bonds are ionic bonds and covalent bonds. And what these really have to do with is how the electrons of these atoms are moving around and how the atoms themselves are kind of interacting. So for example, in ionic bonding, you have that the one atom might be donating electrons to another. And in the case of covalent bonding, they could be sharing these electrons. And why this is important is that we can take atoms and they can be bonded together into specific arrangements, and these form chemical systems. And the arrangements and types of bonds and types of atoms in them all come together to basically give the system specific properties. And that's something of interest to us because it literally constitutes everything that we have around us. And then if we take a look at the specific context of our discussion, mostly has to do with electrons and how they move around and how we can try to describe their behavior and their motion. And something to just take into consideration is that we know that electrons don't move as particles, simply like orbiting the electron, the nucleus, the way that a planet kind of orbits the sun. Instead, they exist as a probability distribution in the space around the nucleus. And we use something called atomic orbitals to describe this probability distribution. So these are single electron functions, and they describe the probability of finding an electron in a specific region around the nucleus. So this kind of illustration here of some atomic orbitals show the probability distribution of finding electrons in specific regions around the nucleus for given states, where the lighter shaded areas or the brighter areas have a higher probability of finding electrons in them. And it's an important consideration that basically we have these orbital functions, and they break up the space around the nucleus and also define the probability of finding an electron in that specific region of space. And then another specific type of behavior that we have to end up taking into consideration is that there's correlation between the electrons when they move. And this has to do with the fact that if the electrons were completely uncorrelated, if two electrons moved into the same region of space, then they wouldn't do anything to each other. But that's not really the case. They exert a force of repulsion on each other. So then we can say that the motion of these electrons is in fact correlated, because if they try to move into specific places, it depends on the positions of other electrons. So this takes us really into now the crux of what is the electronic structure problem. And it's really just trying to describe the motion of electrons in a specific chemical system. And we search for electronic states of interest. So we'll be looking for some specific states with specific properties. And the reason why we do this is that this can really help us gain some insights into the properties of the system. So for example, for specific states like the ground state or various excited states can give us some insight into what is the reactivity of a certain chemical system, and some things like in the spectroscopy of certain systems, we can look at the absorption and emission of light. And that's relevant for things like the development of OLED panels for phones and TVs. We want to know what exactly is the behavior of these substances, and then also some material properties like the conductivity of the materials. So if we can find the states that we're looking for, then we can do an investigation into some properties of these systems. And the reason why we would want to know these properties is typically for industrial applications. And when this would usually be done in the lab, it takes a lot of testing, and it's quite difficult to set up some of the states. And if we can do this efficiently on like computer hardware, and we can narrow down the types of states that we're looking at, and we can prepare them, then we can kind of make the job of the experimental chemists easier, and they can try to validate some of the results. Because also one of the things is that when we perform these computational simulations, they need to be validated in real world cases with laboratory investigations. So now we can take a look at the actual formalism of this problem. So we say that we're trying to look for some specific states, and these states that we're looking for form solutions to the time-independent Schrödinger equation. And this H represents the Hamiltonian of the system, and this Hamiltonian is an operator which describes the total energy of the system, so including both the kinetic and potential energies. And then these states psi are represented with wave functions that describe the probability distributions of the electrons and the specific states of the electrons of the chemical system. And these are what we're solving for. And these are some stationary states where when we apply the Hamiltonian operator to that state, we get out an observable, which in this case is the energy. And another way to think about this, rather than trying to solve the Schrödinger equation, is it's also like an eigenvalue problem. So we have the Hamiltonian, and the Hamiltonian can also be represented with a matrix. And we're trying to find these eigenstates that have certain eigenvalues. And these are the eigenstates of the Hamiltonian operator. So one typical example, which is really well studied, is like looking for the ground states of some chemical systems. And this would be the state that has the lowest energy, or the eigenstate with the smallest eigenvalue. And then if we're going to take a look at the chemical Hamiltonian. So in the Schrödinger equation, we mentioned this, and we described that it's the operator representing the total energy of the system. And this is broken up of contributions from both the electrons and the neutrons. So we have 5 terms in the full Hamiltonian. The first term over here is the kinetic energy of the electrons. And then the second term is the kinetic energy of the nuclei. And the MA is the ratio of the mass of that atom to the mass of an electron. And then the third term is the Coulomb attraction between the electrons and the nuclei. The fourth term here is the repulsion between the electrons, and then we have the repulsion between the nuclei. And if we take a look at an example system set out in a molecular coordinate system, we can see that we have some distribution of electrons in space, and we have the nuclei, and the equation for the Hamiltonian depends on these position vectors of the different nuclei and the electrons. And this chemical Hamiltonian is what we're going to use when we solve the time-independent Schrödinger equation. But something that has to be considered is that it's quite complex to solve the equation in this form. So we have the contribution from the electrons, we have the contributions from the nuclei, and we have the interaction between the two. And we start trying to consider what are some ways that we could possibly reduce the complexity of performing this calculation, and how could we make it easier for us to do this on the computer. And the most common way that's very well used is the Born-Oppenheimer approximation. And what this allows us to do essentially is we reduce the complexity of the Hamiltonian itself. Now, the motivation for this is that when we're studying the motion of both the nuclei and also the electrons, the nuclei weigh a lot more than the electrons that are moving around. And as a result, they move a lot slower. So slowly, in fact, that we can treat them as fixed point charges. So then what we do is we can kind of remove some of the motion, what we can factor it into a different kind of format, but we then consider only the motion of the electrons, and we consider them as electrons moving through a field of fixed nuclear point charges. So when we take this into consideration, we can reformulate our Hamiltonian into an electronic Hamiltonian. And when we do this, we can get rid of the kinetic energy term of the nuclei, because we're treating the nuclei as fixed and not moving. And then we can make the nuclear repulsion term, the term number 5, we can just treat it as a constant that gets added on when we calculate the energy. So what we've done now is we've taken the chemical Hamiltonian and we've simplified it so that it depends explicitly on the coordinates of the electrons, but only parametrically on the coordinates of the nuclei. What that means is when we actually set up the system, so if we go back to this plot here, we have some specific layouts of the nuclei here. And rather than considering these nuclei to be moving around in space and us having to account for that motion in the Hamiltonian through the kinetic energy term, we will fix them at a certain point, and that gives us a distance between these two nuclei. And we would call that layout in the coordinate system a specific geometry, and we would have X, Y, and Z coordinates for each of the atoms in the chemical system that we're studying. And we would then generate an electronic Hamiltonian for that specific geometry, and then we would solve the Schrödinger equation for that specific case. And then what we would do after that is we would then alter the distance between these two nuclei, and we would do the procedure again. And we'll get onto how exactly that's done a bit later on. But all we need to know for now is that the Hamiltonian complexity has been reduced, and now we're going to be explicitly looking for the states, the electronic states that are defined by wave functions of the electrons. So that brings us to one of our next points, which is exactly what form do these states that form the solutions of the electronic Schrödinger equation, what do they look like and how are they defined? So we can kind of find a foundational point to start from, and we would call that the spatial orbitals. And these spatial orbitals are just one electron wave functions that are dependent on the position of an electron. And these specify so the spatial distribution. So they give us the probability of whether the electron exists in that specific region of space around the nucleus. And when we do our computations on the computer, we need to specify these set of orbitals. And we do that using something called a basis set. Now, the basis set defines the functions that we use. And it also defines a computational overhead when we do this. Because if we had a complete set of these basis states, of these basis sets, which are the spatial orbitals, then we would be able to exactly define how the space is laid out, and we'd be able to account for all the different regions that the electron could possibly exist in. But it would also be really, really computationally expensive to do that. So there's different degrees of approximations, those just change the number of spatial orbitals that we use. So how do we factor the region around the nucleus into different functions? And so those give us the spatial orbitals, but then we now need to take into account the spin of the electron, where the spin is like an intrinsic angular momentum description for that electron. And we're going to consider two spins, which is just the spin up and spin down. Sometimes they're also called the alpha and beta spin particles. And it's just a function of unspecified spin coordinate omega. And what this does is tells us the spin of the orbital and then the spin of the electron, and we can form these spin orbitals by taking the product of that spin function and the corresponding spatial orbital. And now, because the electrons have two spin modes, we get two spin orbitals for every spatial orbital that we have. So the spatial orbitals define the space, and the spin orbitals, the spin function defines the spin of the specific electron. And like I said, you get two times the number of spatial orbitals as the number of spin orbitals. Now, when we perform the calculations on quantum devices, the number of spin orbitals that we use is roughly equivalent to the number of qubits that we have to use to encode that problem onto the quantum device. There's specific mappings that we have to use, which we'll get to in the third lecture. But generally, the most commonly used mapping will take each spin orbital and map it to a specific qubit. And these probability functions of the coordinates of the electrons, when we evaluate these, it's kind of just saying, is there an electron there or not when you perform the measurements? And what we end up getting is that these spin orbitals, when you evaluate them, we get like a 0 or a 1. And the 1 indicates that there's an electron occupying that specific spin orbital, and the 0 indicates that that spin orbital is in fact unoccupied. And we're going to use these spin orbitals to build the Slater determinants that we use to describe specific states of the system, the electronic states. And the Slater determinants are used to form the anti-symmetric many electron wave function. The reason it has to be anti-symmetric is so that we have we can enforce the fact that when you swap electrons in your wave function, there needs to be a negative sign taken into account. And it's also this that allows us to enforce one of the postulates of the quantum mechanics, which is the Pauli exclusion principle. And it essentially states that the occupancy of a spin orbital can never be more than 1. So only one electron can occupy a spin orbital at a given time. And that gives us these Slater determinants, which is a wave function that takes in some coordinates x1 to xn of the electron. And then it gives us a specific state that's dependent on the occupancy of the spin orbitals. And these parameters x, it's actually a set of 4 coordinates. So it's the x, y, and z spatial coordinates of the spatial orbital for the electron, and then it's also the spin coordinate. And then that gives us these Slater determinants. And these Slater determinants are then used to construct our full electronic wave function, which we define as just simply a superposition of these different Slater determinants. And what we're essentially saying is that For each slated determinant, which represents a specific state of the system can exist in a superposition of these states. And which this makes sense because of the fact that the electrons move around and have the wave-like behavior. And this then gives us these wave functions that form the solutions for the Schrödinger equation. And something that you can, well, one way that you can think of this is essentially a wave function of functions of ones and zeros, like these slated determinants, and the ones and zeros, like I said, just indicate the occupancy. So now that we've taken a look at how can we reduce the complexity of solving the Schrödinger equation by fixing the nuclei, we can reformulate the Schrödinger equation to get the electronic Schrödinger equation. And this is exactly what we call the electronic structure problem. So we're trying to find the solutions to this problem, which form specific electron states in of the chemical system. And when we applied the Born-Oppenheimer approximation, we removed the motion of the nuclei. And as a result, our wave function depends only parametrically on this position of the nuclei. And that's what I mentioned on the slide here. So the parametric dependence comes into play with the geometries and how we set the geometry of that specific molecule, moving it around and reducing and lengthening this bond, this distance between the nuclei in the chemical system. So we can solve the electronic structure problem, and this gives us an electronic energy for a given geometry of the system. And then we can change that geometry and then solve the equation again. And this gives us another energy. And these energies form the potential energy of the nuclei. And we can put these together to form a potential energy surface along which the nuclei move. So this is an example for the hydrogen molecule. And what you would do in order to get this curve is that you would have your bond length in angstroms, which is a unit of distance. You'd have the bond length, the length between the two nuclei set to like 0.25. You would then define your electronic Hamiltonian and solve the electronic structure problem to get some states. In this case, we'd be looking at the ground state, which was the eigenstate of the Hamiltonian that had the lowest eigenvalue, or the state with the lowest energy. And then we get that as the result and we plot that. Then we'll change the geometry by altering the distance between the nuclei, and we'll solve the problem again, and we'll get another energy. And we continue to repeat this process until we can replicate the potential energy surface. And when we perform this electronic structure calculation, we find the solutions, which are the wave functions that define the states of the system. But what we also really want to do is we want to take a look at the properties of that specific state. And something that you would need to do in order to actually investigate these properties is form the density matrix that represents that state. And that's something that people do after solving this equation. And that basically covers everything in the first lecture. So the first lecture's purpose was simply to give an introduction into the electronic structure theory and give us all of the tools that we need to know in order to move on to trying to solve that electronic structure problem, which is trying to solve the time-independent Schrödinger equation. And what we take a look at in the next lecture is specifically trying to solve that using some classical methods. And yeah, that's basically everything that we were going to cover today. And I hope that it was understandable. And if you had a little bit of trouble following along, there's some additional resources that are quite useful. So the one is this textbook on modern quantum chemistry, and it goes into an introduction of electronic structure theory. But the first chapter basically covers everything that we've done in this lecture today. And then another really useful resource is on YouTube. There's the lecture series by Artur Ismailov, at the University of Toronto, and he covers these types of topics in depth. And if you wanted to look ahead towards the next lectures on the quantum computing applications for this, he also goes into that in his lecture series. And thank you. That's everything. It ran a bit quicker than I expected.
Well, okay, Shane, thank you very much. It was really an excellent introduction, and I see lots of claps coming up the screen. Since we have still some time, are there any questions from the participants that you would like to ask Shane? And you're welcome to raise your hand, and we can give you the right to speak. Any questions in here, in the room?
Show this state representation. Give me like please the example because it was like parametric.
Okay, yeah. Oh, so the state you mean
State representation.
Yeah,
Here.
specific one.
That would be
Okay.
nice to have some.
So
ideas.
I don't have any examples that I can show here, but as one to describe, if you had let's say you had like a hydrogen example, right? You had H2, H2 in the minimal basis set, you'd have 4 spin orbitals. And you have some possible configurations, and it would basically be that you would take the 2 electrons and you'd move them around spin orbitals. And the way that you visualize that is if you had 4 entries here, you could, if there were no electrons, it'd be 4 zeros. And if you had the 2 electrons occupying those orbitals, then, for example, one possible state would be 1, 1, 0, 0, which is occupying the first 2 spin orbitals. Another one would be that if you moved 1 electron to another orbital, it could be like 1, 0, 1, 0. And those form specific states that you can measure. You perform a measurement of that chemical system and of the state of the system. Then you get that binary string telling you that there was an electron in this specific spin orbital, or this other orbital was unoccupied, and there was maybe an occupation somewhere else. And that's just one specific electron state, and you get that from one measurement. But because of the fact that the electrons are moving around as a distribution, we have the wave function as the superposition of these states. So it could be for example, let's say you have the superposition where it was some complex coefficient C1, and then the states 1, 1, 0, 0. So you have the probability C1 of measuring the system in the states where the electrons in the first 2 orbitals, the next 2 spin orbitals are unoccupied. And then you have another possibility of the coefficient of C2, and that could be, let's say, the states 0, 0, 1, 1. Where it was
Specific example, you have 16C.
Yeah. Yeah. So
Combination of 2 to the power of 4.
Exactly. Yeah. So the number of possible states that can exist in your wave function is equal to the number of basis states in the Hilbert space of your chemical system from the Hamiltonian. So if you have, I could say, 4 spin orbitals, and it's 2 to the power of 4 possible states that you can measure when you measure the system. And those states correspond to specific electron configurations. So if you're looking for the ground state, what you're trying to do is trying to find the most stable configuration of the electrons so the energy is as low as possible.
Any other question? I think there are only compliments online. Yeah. But no questions. Then, there is not one question now. Thanks a lot, by Eugene Fouché. Can you maybe elaborate on how this is applied to chemistry? And I
Okay, so if I just go back to here. Okay, so one specific type of example would be that if you had a chemical system and you wanted to find out the reactivity of that system in a certain state, what you would want to do is you'd want to formulate the Hamiltonian for that system in a given nuclear geometry. And then you would try to find that specific stationary state that you're looking for, let's say the ground state. And once you found that ground state and you've formulated the density matrix for that specific quantum state, you can do investigations into properties like the reactivity. Why that might be useful for chemical applications is trying to understand like reaction rates or something like that. Another one is the various excited states that you can look for. So if you try to find, if you solve the Schrödinger equation to find a specific excited state, that might be something that's useful, like I said, for OLED design, because it helps you understand the band gaps and stuff like that, and you can understand the light emission and absorption. So I hope that helps a bit. I think that it's quite, if you just Google like applications of electronic structure problem, a lot of them can come up, and they have a lot of industrial applications. But basically, they all tie back to chemistry. And what you'll typically do is you'll do this type of computational simulation, and then you'll get some information out. And then once the experimentalists are reasonably sure that this forms a good like a good modeling, they would then try to replicate that in the lab to validate the model.
Another question. Out of curiosity, would there be a way to explain the quantum chemistry of their annihilation of matter and antimatter using quantum computational models?
I'm not sure. that question went a little bit over my head. So I'm sorry, I'm not much use for that. So.
And we formulate the question more precisely the next lecture.
Yeah. So yeah, I'd be happy to try think about this and then get back to you in the next lecture.
But the question is that quantum chemistry is very good. Hartree physics, I guess.
Sorry, did finish there? Yeah. Okay, we will.
Yeah, there's a paper.
We will think about it. Yeah, we will think about it. Yeah.
Okay, thank you.
So if there are no further questions, then thank you very much, everyone, for attending, and we hope to see you all again next Wednesday, and where it will become probably more serious. Yeah. So thank you very much, everyone. Have a good afternoon, and we will see you again next week. Thank you, and thank you, Shane. Thank you very much for the big effort. Yeah, thank you very much. It was really very nice. Thank you.